Okay, we're back. This is Clinton Weir. I am discussing my final project for CSC 535 at University of Illinois Springfield for the spring of 2024. My final project. Earlier we were discussing my display functions block. I had a little bit of difficulty because the display random images function was returning some odd results. I was trying to figure out why that was. So I figured out the problem. So actually, I'm not sure if I figured out the problem exactly. I think I fixed it. So the problem was that the images were two images classes were reversed. I had padlocked images, have unlocked. I think it was padlocked and unlocked images. The labels were reversed. Now that wouldn't crop up. That shouldn't crop up later because the actual labels and the predicted labels would both be reversed. So, if it's being trained on the images being the labels reversed, then it predicts the labels being reversed, and the then the actual and the predicted labels will be, if they're both reversed, then your accuracy will be reported the same way, as long as both the test and the the training and the test sets, if the labels are reversed in both, it's like they weren't. So the thing that was confounding me earlier is this category list, where I have discus. I know that the categories are supposed to be alphabetical. So I was confused because my list was not alphabetical. I had discus, multiple, unlocked, and padlocked, and so on. So I noticed this. I was thinking, well, unlocked and padlocked are reversed, but it's because these are not the directory names. For whatever reason, for the category unlocked, I had the directory name is nozip. So earlier I saw that and I corrected it. I saw the category list was not alphabetized, so I corrected it. I reversed unlocked and padlocked. So then later I ran this code, the imports. I ran the display function code, and I noticed the some of the image labels were incorrect, and I figured out they were reversed. So then I fixed my mistake. I figured out the mistake and fixed it, and I still the images were showing up with the wrong labels. So I dunk and thunk, and turned out I just needed to restart my kernel. Probably there's a better way, but that's what I did. And so now I have my labels and my images matched up. Maybe it doesn't matter because I don't plan to reevaluate my Jupyter notebook, but I've got that debugged. So now the subject of this video is this block about confusion matrices. Not sure what this is about NumPy. because I'm sure that NumPy works fine. So we've talked in the first video. We talked at length about these functions. This sklearn is a method I found to make a nice. Well, sadly, I don't have. Sadly, I don't have an example right here in my in this notebook. But it makes a nice looking confusion matrix where it makes a nice looking one where it's a graphic and the labels are displayed on the graphic, not an integer, but the actual labels. So that's great. The thing we were doing before I brought this stuff in, the thing I was using, sorry, no, the Seaborn is the thing that draws this graphical, nice looking confusion matrix. This calculates the confusion matrix. But anyway, so display confusion matrix, you call this function with your model and your data set, and it will figure out do the math, the logic to create the confusion matrix. That is a matrix that shows for each true category, it'll, on one side it shows the true class, and on the bottom it shows the predicted class. And so, for example, suppose there are 100 images of discus locks. It's got 100 images of discus locks. Maybe 90 of them were predicted to be discus locks. So suppose 90 of suppose that 90 of the discus locks were classified as discus locks. So it'll show a 90, and that'll be at a part of the diagonal. I think in my case it's the upper right, the far upper. Sorry, it'll be the far upper left along the diagonal, and so it'll show in that spot. It'll show the number 90 because that's the number of actual images of padlocks that are classified as padlocks. And then maybe 10 of the images of padlocks were classified as an unlocked unit. So in the column that corresponds to unlocked storage units, and the row that corresponds to discus locks, then you'll see that I think I said 10. You'll see whatever the number of actual discus locks that were classified. Did I say as unlocked? Yeah. But anyway, so it'll at the intersection of the actual classification and the predicted classification, where those intersect, then you'll see the number that correspond to that actual label and that predicted label. That's a confusion matrix. And so you, for this function, you pass it the model, you pass it a data set. So, we have 3 data sets. Unfortunately, this code does not work I think I figured out why, and you can listen to the first video to hear way too much about that, and a lot of me humming and hemming and humming and thinking out loud. But it doesn't work for those. It only works for the test data set. I might, if I have the time, which I do not expect to have, then I might fix it. Like, I could put train sorted and just copy, paste, and then what I decided was it's probably this flag here. Just paste that flag in, validation sorted, just paste that right in with that, and then add that flag. And I think that'll fix my problem. I'll have to pass the correct, I'll have to pass the right data set, but I think that'll correct the problem. So here is, we're getting the length of the data set. That is the number of batches into which the data set was split. That's the number, oh gosh, I think it's the ceiling of the quotient of the number of images divided by the batch size, the ceiling. But in any case, the length sub data set is the number of batches in the data set. And so this becomes a list of the true classes. And this is a list. This is a list of lists. So each batch, and I'm thinking there's probably a better way than what I'm doing here. But each batch, there will be a list. For each batch, there is a list of the true classes, and that'll be in integer. So the true class being the for each image, what is in the image? Is it a discus lock, etc.? Although it's not going to be the string, it will be an integer. And then in the next, I just combine those lists, so it's one long list rather than however many short lists. Simple enough. And then to get the predicted probability, you use the predict function on the input model. You call the input model with the predict for the, gosh, how do you say that? In OOP, you send a message to the object, is how you say that. You're calling the object method, and you're passing the data set. In any case, that data set is all the images and then, so if you use the model on the image, you're not gonna get the class into which the model class. It's not the class. It's a list of probabilities for each class. So you'll have five floating point numbers. Suppose that the model is just 100% certain that it's a discus lock. Discus lock happens to be the first number in it happens to be associated with 0, the index 0. So if it's 100% certain that the image is a discus lock, then the list will be 1 0 0 0 0. And in that case, the next line of code would classify that image as a discus lock. And hopefully, if the model says it has 100% certainty, hopefully it is a discus lock. Yeah. So I've tipped my hand. This line of code, argmax, is going to tell you the index of the float that is the largest of the 5. So if the first float is the largest, it'll return the index 0 because for whatever reason in computer science we like the lists indexes to start at 0. For many contexts, that's what we do. Obviously there's reasons for that. And then so we have a list that's going to just say, is the true class equal to the predicted class? It's going to do that for the entire list of all of the images. Is the actual class for that image, does it match the predicted class? And so based on, and I don't actually use this. This is an artifact. Apparently, I hope. Wait. Let me double check. Yeah, that's an artifact. I assume everybody does this, but I write code and then I edit it, and something I'm trying doesn't work, so then I delete parts of it and I try something else, and I constantly end up with code artifacts. Anyway, so the confusion matrix, it's a grid of numbers, in this case integers, and in this case the rows correspond to the rows and columns correspond to our classes. The rows correspond to the actual classes of the images. We talked about this already. And the columns are the predicted classes, and it's just a grid of numbers. I think it's a list of lists. In terms of data structure, not certain. And then we print it, and it just comes out of looking like a list of lists. It's just an ugly looking, it's just text. So then this, I found this this heat map thing in the Seaborn library, and we're going to see that later, I assume. But it's a pretty nice graphic, and you'll see the X tick labels and the Y tick labels. The argument, the input, I don't know, whatever you call it, the input for the argument. We're passing the category list, which comes from loading images, is where I kept that, and it's the text version of the classes or the labels. So what you end up with is this nice graphic that represents the confusion matrix and has the labels, whereas this text version, it doesn't give you even the integers. It doesn't even show the integer labels, the integer version of the classes. It doesn't show that. It just, you're just supposed to infer which row and which column corresponds to which integer, and what that correspond, which label that corresponds to. This is much nicer. It's a huge quality of life improvement. And then this last piece is really, it's really another artifact. It's functional, but it's not here because I need it to be here. The reason I wrote this was because, I was obviously getting confusion matrices. It seemed, let me say, quasi-obvious that the confusion matrices that I was getting did not agree with the output of the evaluate function when called. Again, when I called the model object, when I called the model object's evaluate function against a particular data set, it didn't match up. The accuracy that came out of the evaluate function did not match up with the confusion matrix for that model and data set. And so because of this discrepancy, I added this bit of code to add up the accurate versus the inaccurate according to this confusion matrix, according to this basically comparing the true class up here to the predicted class down here. That's what this does. This calculates accuracy, and this confirmed that the evaluate function did not match the confusion matrix if it needed confirming. Sometimes you do dumb things just because. Sometimes you do dumb things when the computer is doing dumb things. To make sure that you haven't lost your mind, I guess. When I worked in QA, we called this we didn't call this exactly, but we had something called a sanity check, and this piece of code is sort of that way, and it's sort of, have I lost my mind? This is what accuracy is, right? This confusion matrix really is not showing me, the accuracy that I'm expecting. I didn't need to do this. I was just getting frustrated. I was just getting frustrated. But in any case, so that's why that is there. I could take it out. It's not hurting anything, so I have not taken it out. I don't remember what this. There's parts of this function here I'm just seeing. I don't really remember why it's there, but I don't know. I don't remember why some of these arguments are there and what they do. All right, moving on. Validation confusion matrix. This literally just is a convenience function to create a confusion matrix for the validation data set, and then the display confusion matrices is if I want to see all three. Both of these functions could go. But let's validation. Where? I'll need to import train sorted and validation sorted. Should I make a new line? Test train sorted and validation sorted. And I think the way that Jupyter works, even though I have not evaluated that code, I'll be able to come down here and it'll allow, yeah, see, that's probably not the best because it'll mislead you into thinking that you've evaluated code to define things that you haven't evaluated and you haven't defined. But alas, I think this might fix my confusion matrices for the training and validation data sets. And after I get done making this series of videos, and after I have created my submission, after all of that is done, then I will take another swing at some of this stuff. Some of this stuff that I'm working on. These things, some of these things that I'm improving as I go through. I'll have a chance, perhaps, to redo, to reevaluate the Jupyter Notebook and see these improvements. I don't think I'll have anything to come back to, but in the next video, up until now, each video I've kind of gone back and shown how any corrections may have turned out. I'm not going to do that this time because I am not going to go through and reevaluate the entire notebook. But we'll move on to the next step where we'll be starting to build the model. Let's see. And I probably will move this model component definition. I'll probably move it down to the next title. Let's see, so right now it's in this preparation section, and then I'll probably move it down into the, nah, it's fine where it is. I think it's fine where it is. Okay, but we will come back and discuss that in our next video.